Okay, yeah, I guess I'll start here. Yeah, so it's joint work with Volker, who's here. It's this guy, and Omar Fazi. He's actually visiting Caltech this semester, but otherwise he's based in Lyon, and Volker is at ETH. So this work is kind of based on 3 different drafts or papers. So the first one is this quantum-proof randomness extractors by operator space theory. This is a paper that was also mentioned in the previous talk. By the way, thanks very much for setting up the stage in the last talk. I can go through my first slide pretty quickly, probably. And the second paper is in the TQC proceedings. It's called Semi-Definite Programs for Randomness Extractors. Yeah, it's not yet published, but you can find it on Omar Fazi's homepage. And the last one we call Quantum Bilinear Optimization. And if everything works out, it's actually going to appear tonight. So yeah, this talk is mostly based on the framework or the way we talk about these things in the last paper. OK, so let's start. So yeah, I want to analyze quantum adversaries, and for this talk, mainly quantum adversaries for randomness extractors. So let me just say a few words about these extractors very quickly. But again, we had this overview talk, so I don't need to go into any detail. So we want to transform some weak source of classical randomness into uniformly random bits. Okay, so we have some input X, output Z. And well, this is important for application in cryptography, computation, information theory, and so on. There's a whole classical theory of so-called pseudo-randomness. And yeah, so this talk is about analyzing what happens if we add an observer, an adversary with a quantum memory. So what is a quantum adversary? It's just an adversary or an observer with a quantum memory. And this is motivated by, again, some possible application, post-quantum cryptography, quantum cryptography, or device-independent cryptography. Also, maybe for applications in multi-party quantum computation or in quantum information theory. Okay, so what's the model? So we have some input source. It has some randomness in it. And as was mentioned in the last talk, we want to measure this with the min entropy, or in other words, with this guessing probability. So I just call it guessing probability. But it's actually the maximal value of the input distribution. It's also how well you can guess the distribution, right? And so I want to assume that we have some randomness, so the probability that one can guess the distribution is not too big. And then we want that the output is almost fully random. And the measure of what almost means is this variational or statistical distance. OK, so what is a randomness extractor? So the type of setup I'm going to look at in this talk is the following. So a randomness extractor is a family of functions. OK, so we take D functions. And they go from the input alphabet to the output alphabet. And we call this family of functions a K-epsilon extractor if for all input distributions that cannot be guessed too well, the output is almost uniformly random on average over all functions. Okay? So this is also called a strong seeded randomness extractor. Okay? So this is the type of setup I want to analyze in this talk. So intuitively, just if one cannot guess the input too well, then the output is nearly perfectly random. Well, it's a nice definition, right? Do these objects actually exist? Yes. So we can choose the output size as large as k, approximately. And k is the bound on the input guessing probability. So how well we can guess the distribution to start with kind of determines how large the output we can choose. Okay, now let me also mention that this extractor property is computationally hard to decide. So given a set of functions, is it a K-epsilon randomness extractor or not? This is a computationally difficult task. Okay, so that's a randomness extractor. Now again, I want to bring in quantum adversaries. So we have some observer. And this observer is assumed to have a quantum memory now. And the question is, can we also distill some randomness relative to this observer? So if the observer has some prior information about the distribution, can we make the output after we applied the extractor, uniformly random and private. And so now, how do we model this quantum site information? So now we just start with a bipartite thing. So we have the distribution on X, and then this quantum memory, the E system, and this can be modeled as classical quantum states. So this is just a distribution on X we want to distill from, and this is the state in the quantum memory of the observer. And now again, the extractor is still the same. It's still a family of deterministic functions, a family of D functions, but just now we want that if the adversary cannot guess the distribution X too well, then we want that the output is uniformly random, but also independent of the E system, again, on average over all functions in this set D. Okay? So that's what is called a quantum proof extractor. And then now I would like to compare these two conditions, right? So this is the condition for a quantum proof extractor. This is the condition for an extractor. And well, the first one is kind of stronger because if I just put like a one-dimensional quantum memory, right? If I choose the E system to be one-dimensional, then the condition is the same. But in general, this is more to ask for. So how do these two things compare? That's kind of the question I would like to analyze. And so let me also make this comment here that the quantum proof extractor property, this first property, we don't even know if it's computable. So given a set of functions, is it a k epsilon randomness extractor that is quantum proof? We don't even know if this is computable. And the reason is that here, on this E system, this quantum memory, we don't bound the size of the quantum memory, okay? So the only bound we ask for here is this guessing probability bound. So in particular, he could have like an infinite dimensional quantum memory as well.
For this hardness property?
This one? Well, okay, so there's no like real hardness result. We don't know. I mean, you would have to show that it's computable. That's all I'm saying. We don't. I'm not aware of any proof of that. Or what's the? So given there is a, okay, I'm not a computational complexity guy, but given a set of functions, so these are just deterministic functions from some like input alphabet to some output alphabet. And given those, I would like to know. Sorry, what was the comment about?
It's just not possible for a fixed family to compute.
So yeah, I give you a set of functions. I write it down on a sheet of paper, and then you tell me, is it a k epsilon quantum proof extractor or not? That's yes. Okay, good. So yeah, so this comparing these two conditions is an operational example of studying the advantage of a quantum memory, right? So here, one time we have a quantum memory, one time we do not. And this is, I think, very similar in spirit as an analysis of classical and quantum or entangled values of two-proof games, or also similar to communication complexity or even computational complexity questions. So I really want to kind of study the gap between these two conditions from a theoretical viewpoint. Okay, so we have seen these kind of results before, I think. So this is what was done before. So it was shown that for many explicit extractor constructions, so for many set of functions that are extractors, quantum proof is actually the same as being an extractor. Yeah, so I don't want to go into any details here. Again, this counterexample by Gawinski. So there are constructions for which quantum proof is different from just being a classical extractor. Namely, there is this construction for which the quality of the randomness, the error, increases at least by a like multiplicative factor that is linear in the output size. Okay. And now in our work, we would like, as I was mentioning, to understand this classical quantum separation better. And we would like to find bounds on this gap. Okay, so this is kind of a lower bound on the gap. We know that the quality of randomness can decrease by that much, but we would like to understand this more generically, basically. And the message here, kind of the take-home message, is that at least these stability results from up here, they can more or less be understood from so-called semi-definite program relaxations. So these are semi-definite program relaxations of the quantum proof extractor property. I'm going to talk about this now. So we start with the classical extractor property. So again, I have given a set of functions, and I want that if I cannot guess the input too well, then the output on average over all functions should be almost uniformly random. Now, in other words, I can also write this as this expression over here. So I can optimize the distance to the uniform distribution over all inputs, over all probability distributions that I cannot guess too well. And then I call this C, okay? So C is kind of, maybe we can call it classical value of the extractor. And if this value, for a given set of functions and given k smaller than epsilon, then I know I have a k epsilon randomness extractor. And so the title here is bilinear optimization. So of course, the thing I want to talk about here is that I can actually write this classical value of the extractor as a bilinear optimization with linear constraints. Okay, this is it's pretty straightforward to see here. So the variables here are px and b s of z. So maybe maybe you look at this objective function first. Okay, so I can just write out this one norm. So in particular, I can write it in terms of its dual norm, the infinity norm, and this corresponds to this optimization over these b variables. Okay. So this is how I get from this expression here to this expression. I just write the one norm in terms of the dual norm. And then we have these conditions, these linear constraints. And well, the p constraints exactly comes from this rewriting I was just talking about. The other constraint here is exactly this guessing probability constraint, right? So the guessing probability not being too large means that, well, it's a probability distribution, so it's lower bounded by 0. And the largest entry should be at most 2 to the minus k, right? That was the definition of this. And OK, so here I relax the condition a little bit. I look at the subnormalized distributions as well, not only normalized ones, but the value of the program can be shown to be the same. OK, so this is about the classical extractor property. So it's not exactly what we would like to talk about here, or what I would like to talk about, but I would like to talk about this quantum proof extractor property. Now, what one can do with this bilinear optimization is one can kind of quantize it. Okay, so here the variables are just real numbers. Okay, the variables we optimize over. Now one can quantize these programs by making these variables, so the px and the psz, one can make them non-commuting, so one can think of them as operators on a Hilbert space. Okay, so how do we do that? So this is again the classical program from before, and now the quantum version of that, the non-commutative version of that, is given by this program. Okay, so I call the value, the optimal value of this program, I call Q now, for reasons I'm going to tell you in a second. But let's look a bit at this program and how we can get it. So why is this the non-commutative version of that? So first, the maximization here is now over Hilbert spaces. So H are Hilbert spaces. And again, these are Hilbert spaces. So there's no bound on the dimension. Okay, so there's we optimize over all Hilbert spaces of any dimension. And then these variables here, the rho x, the bsz, and the sigma, these are now operators on this Hilbert space. Okay, so before we just had these real variables, and now we have operators on this Hilbert space. Okay, now the objective function, first part is still the same. The second part here, you can see we no longer have this the product of these two numbers, but now we have this Hilbert-Schmidt product of these two operators. Okay, so these variables become these non-commutative values over here. And again, okay, yes. Now we have these linear constraints, and here, yeah, it would take me a bit of time to motivate this properly, but let me just tell you that if the non-commutative version of these constraints, they look like that. Now, okay, so this is the non-commutative version of this program, but why are we interested in that, right? Because what we're interested in is this quantum-proof randomness extractor condition. So we want to know when, for a given set of functions, this condition is fulfilled, right? We want that if the adversary cannot guess the input too well, then this is small. Now, of course, what we will show, or what we show in our paper, is that the optimal value of this non-commutative bilinear optimization is corresponds exactly to the quantum-proof randomness extractor condition. Okay, so this value, which I call Q, if this value is smaller than epsilon, then I have a quantum-proof randomness extractor, K epsilon randomness extractor. So basically, what's happening here is that, again, the optimization over these operators P, like in analogy to what is happening here, if this kind of corresponds to an infinity norm here, and if we write it again in terms of this dual norm, then we get this one norm condition out. If we actually do the optimization over the B, then we get this one norm condition out. And this constraint here corresponds to this guessing probability constraint. Okay? Let me just say that. Good, so what do we have now? Well, now we know that if we want to understand the gap between extractors and quantum-proof extractors, we can just study the value of these bilinear optimization programs, the classical value and this quantum value. So now the problem is, I was mentioning that before, that for this quantum value, we have to optimize over all Hilbert spaces. Okay, we have to optimize over any dimensional Hilbert space. So how do we actually do this? Because it's a kind of an unbounded thing, right? And what one can do is or what we do is we can give a semi-definite program relaxation hierarchy that gives upper bounds on this quantum value. And moreover, this hierarchy is also asymptotically converging. Okay, so I can upper bound this quantum value with some semi-definite program, STP1, and then I can add some constraints to get a larger STP, to get an STP2, and it's always smaller than the first one or not larger, so on and so on. And if I go to the infinite level of this hierarchy, I actually get back this quantum value. Okay, so this is very much inspired by work of Lasserre and then the non-commutative extension of this work by Piranio and co-authors. And this is about general polynomial optimization. So it's where we took our aspiration from. And now the thing is, these STPs, okay, at least the lower levels, they're efficiently computable, okay? So this hierarchy actually gives an efficient criterion for when an extractor is quantum proof, or even when like a given set of functions is an extractor, right? So because if we compute, so I give you a set of functions, then we can efficiently compute this first level STP, let's say. And if this is small, it's like smaller than epsilon, then we know that also this Q value and this C value is small. So of course, this might not be a tight bound here, tight upper bound, but if this is small, then we know that we have a quantum proof extractor. So I want to tell you in a couple of minutes a few ideas how we come up with this, but maybe first a few words about what this now means for extractors, okay? What does this hierarchy mean? So basically, we can understand the stability results I quickly mentioned before already from this first level STP relaxation. So for example, we can show, so this is a generic bound, so it holds for any set of functions, okay? So we can show that the value of this STP is smaller than the square root of 2 to the m times the classical value, okay? Of course, the STP value is also bigger than the classical value, okay? So if m is small, if the output size is small, constant output size, then we see that any extractor is also quantum proof, right? Because if you have an extractor, then you know that the C value is small. So you can see if m is really small, then you also know that the STP is small, and by that the quantum value is small, so you have a quantum proof extractor. Yeah, this is kind of an extension of what was mentioned in the last talk, where it was said that if you have a 1-bit output extractor, it's stable. So here you can put in more like 2 bits or 3 bits, just small output. Okay, then there's the second generic bound one can get from the STP relaxation. So here, again, for any set of functions, or for any extractor, the STP value is upper bounded again by the classical value, and then, okay, this kg is just Grothendieck's constant. It's like it's a constant, and this factor 2 to the n minus k. So if there was already lots of randomness in the input, so if the input distribution was really hard to guess to start with, if you look at the scenario like that, then your extractor, if you would apply an extractor, then it's automatically quantum proof. So these bounds are not like very strong, but they're like generic bounds, so they hold for any set of functions. And one can also study examples. So for example, this most famous example, 2 universal hash functions, for those also this upper bound, this STP upper bound relaxation is actually is tight. Okay. Good, so that's basically for now what you get out of this hierarchy for extractors. Now how do we get this hierarchy? Okay, so let's start again with this quantum program, right? I want to find upper bounds on the quantum value, the optimal value of this program. So the idea is to find a relaxation of this bilinear form here. So bilinear form means it takes 2 operators on the Hilbert space we're considering, and it outputs a number, right? It multiplies them and then takes the trace of it. Okay. So now the idea is that we can see this bilinear form as part of a gray matrix. Okay. So I call this gray matrix omega 1. It's defined. The entries are just a trace of x, u, x, v, where these x operators are just either the row x's or these operator b's. Okay. So I just go through all of them. So if the u is an x, it's a row x. If the u is this S set, then it's just a b. Okay, so now this matrix has these 4 blocks. Okay, so I take inner products of xu and xv. So on the left upper side, I have products between row x prime, whereas here I have products of b's. And here on the off diagonal, I have mixed blocks. Now the point is that this matrix, well, it's a gray matrix, which means that it's a positive semi-definite matrix. Now the idea is just instead of maximizing over all Hilbert spaces and operators on these Hilbert spaces, we just optimize over positive matrices of this form. So we just replace this optimization by an optimization over all matrices omega 1. I mean, all positive matrices. And of course, it's a relaxation then, because for any possible choice, we can define a matrix that is positive. And we have to add a few more constraints, or we can add a few more constraints. So in particular, one constraint is that this upper left part here, it's also entry-wise positive, right? So these row x's, these are the quantum states of the adversary in his quantum memory, and these are positive operators, so this is a positive number. Okay? And moreover, of course, we also have these constraints down here. We cannot see them right now, but one can also formulate these positivity constraints. And these are positivity constraints on this matrix omega 1. Okay? So if we replace this maximization just by a maximization over all positive matrices omega 1, for which this upper left block is entry-wise positive, and for which all these positivity constraints, these additional positivity constraints hold. I didn't tell you what those are exactly. Then we exactly get this first level STP relaxation. Okay, and then you can also go to higher levels by using this ID. So basically, you just look at higher order products of these variables, right? Before we just had look at products x, u, x, v. But now, if you want to go, for example, to the second level, you have look at products of 4 variables, and then by inspection, one can also see that this matrix omega 2 is positive semi-definite, and so on and so on. So if one does this really systematically, one gets this STP hierarchy I was telling you before, and it actually converges asymptotically. So you get back the quantum value asymptotically. Okay, now I was also saying that this work was inspired by this work of Lasserre and Pironio, and this non-commutative version of polynomial optimization by Pironio, it's actually called NPA hierarchy, and I just want to stress that the hierarchy we get here for this extractor setup, it's a bit different, so it has additional constraints compared to the NPA hierarchy. So it's in that sense tighter. And for example, here in this setup, these additional constraints, they give us that the nth level, also for any n, of this RSTP relaxation is actually upper bounded by 1, which is a natural property because of the quantum value, of course, is upper bounded by 1. So if one, I mean, it's also possible to use this NP hierarchy. I mean, not directly, but it's possible. But then it's not clear if one gets this property. OK, so that was basically what we did. Now one could, of course, do much more. So what I would like to do also is study the higher levels, in particular the second level, a bit more of the hierarchy, and what it tells us, because all the bounds I gave you, they also already follow from the first level. And maybe it's also useful for constructing new quantum-proof extractors. And more fundamentally also, maybe it's useful for analyzing how large this classical quantum separation can become, right? So I gave you this example of Kavinsky, for which we know that there's a separation that is of order m, so meaning that the quantum value is bigger than m times the classical value. But it's a very small separation, and in practice, this doesn't matter. So one can ask, can there be a larger separation? And so I would say that probabilistic extractor constructions are a good candidate for that. And one could, for example, try to study this, the hierarchy for these probabilistic constructions to learn something about possible gap. OK, so that's the last point here. This whole setup about bilinear optimization, one can also apply it more generally, not only to randomness extractors, but for example also to, well, study two-proof games, to study the separation between the classical and the entangled value. This is very similar to this NPI hierarchy, but as I was mentioning, we have these additional constraints. So maybe there's something to be learned for games as well. Then one could also apply it to randomness condensers, kind of a generalization of extractors, also mentioned in the last talk. One can apply it to channel coding. So here the quantum value corresponds to entanglement-assisted channel coding. And yeah, so there's also there are also these other type of optimization programs where there's an optimization over a so-called completely positive semi-definite cone. And our hierarchy also applies to this type of problems. OK, yes. Very last comment, there was this paper appeared last week. It's a nice paper. And basically what they do is they derive the first level of our hierarchy. OK, so they say, OK, the first level is a relaxation of the quantum value. But they don't have a hierarchy. They just talk about the first level. And they talk about it in the setup of two-proof games. OK, so now I'm done. Thanks.
Like the product of two operators in the group, like I'm not saying the group itself only consists of very small.
So which bounds are you talking about now? The generic bounds, you mean? Like this 2 to the m and n minus k? Yes, yes. So how this is done, basically, is the question? That it's only a product of two operators, you're saying? Or I'm not sure. You mean for two universal hashing? Yes. Two universal hashing, yes, yes. Yes, you can, yeah, okay, yes, you can say that's, I mean, like this, it certainly works. Yes, it's not, I mean, the 2 norm is not exactly the first level, but yes, if you have a bound on the 2 norm, then the first level will be bounded, yes.
You can just use the like degree 2.
Yes, yes. Yes. Oh, yes.
Maybe one quick question on the
Yeah, so if I'm understanding correctly, the situation for convergence of this hierarchy is similar to the NPA hierarchy.
Yes.
That you know asymptotic convergence, but not a rate of convergence.
Yes.
Okay.
Exactly.
Is it, should it, I mean, should we believe that they're related, like, for NPA, would it apply here?
Yes. So if you go to the 2nth level of our hierarchy in general, then you get a bound at least as good as from the nth level of the NPA. So there, I mean, it might even go in the other direction. So the answer is yes.
Okay, let's thank Mario again.